All right, let's get started. So we're starting part 4, I guess. We're starting homework 4 content. So I guess part 4 of the assignment, or module 4. I don't know what to call them. But homework 4 is pretty easy. You should all get credit for homework 4. I know homework 3 is very difficult, especially judging by the number of submissions are extremely low even. So many of you are just relying on the late deadline. You know, that's fine. That's your decision. It's not what I intended, but it is what it is. But I know homework 3 is tough. Homework 4 is letting off. I think I said this last time, but homework 3 is like I see it as like the final exam of the course. That's your final challenge that you need to complete to pass the course. Then the rest of it's AOs, the rest of the way down. So homework 4 is just the application objective. There are no learning objectives. If you're just trying to pass the class, you know what you have to do. That's nothing for homework 4. But this is where you can earn a few more application objectives to get your way towards the A. And I think this is one of the easier application objectives, or one of the easier objectives overall in the whole course. Mostly because on this Friday, I go through a whole tutorial. I walk through exactly what you have to do with this. If you just follow along that tutorial, there might be, you might run into some strange bugs. That always happens from time to time. But if everything goes smoothly, you can get it done probably during lecture on Friday, if I'm being honest. So that's homework 4. It's deploying with HTTPS, and I forgot to add secure WebSockets to this, so WebSockets is not a requirement for this one. But it's adding HTTPS to your web server. Yep.
Is it more difficult to do with secure WebSockets?
No, you literally just add the character S in the string where you're connecting to your WebSocket. I just forgot to add it, so it's not required, but it's not a big deal either. It's literally in the string where you connect to WebSockets on the front end in the JavaScript. Instead of WS, you do WSS, and that's it. I gotta chill. I know we're excited homework 3 is over, but y'all gotta chill. Man. Yo. It's 3. It's always 3-week chunks. But that said, the last week, these last 2 lectures, I don't assess anywhere. So 7 lectures for everything. For the homework, for homework 4, 3 lectures. For project part 4, 7 lectures. So project part 4 is so the rest of the content, like homework 4. Let me restate that. Let me reword this in my brain. This week, after Friday, you're going to have everything you need for homework 4. Homework 4 isn't meant to be very complex. It's pretty straightforward. And there's very little coding, actually, for homework 4. It's more configuration. It's some extra Docker configuration to set up Nginx. It's running OpenSSL to generate your self-signed certificate. Again, your public and private key, installing them into Nginx. It's really just configuration. Almost no code. You probably no code at all. And then the rest of the time is the project. Objective 1 on the project is going to be basically homework 4 plus a bunch of extra stuff. So this homework 4, part 4 content of the course, these next 3 weeks, really will start shifting towards your project. And since the homework's only application objectives, project parts 2, 3, and 4 are all only application objectives. It's all application objectives for this last part of the course. So project part 4, the first one's deployment and encryption. I thought that said development. I thought I had a typo right in the first word. Deployment and encryption. You will deploy with a domain name, get a valid certificate. The homework's going to be a self-signed certificate that you're going to generate. This one's going to be a valid certificate that you're going to get signed by a certificate authority, and deploy your app out there on the internet. That's your task for part 4. This one I did not forget about WebSockets, so you do have to add that extra S in your front end for what it's worth. And your deployment has to, work. It has to be deployed to the internet, to the world. And then in your README of your repo, somewhere in your README, make sure you get your domain name, because we're not really going to know where to look on the entirety of the internet to find your app. So in your README, put a link to your app, somehow get your domain name, get your URL in there, so we can know where to find your app, because we're going to use your live deployment for grading for Project 4. You have to maintain this live deployment, and that has to be up and running from the Part 4 deadline onward. It has to be live and working when we go to grade these things. So that needs to be maintained as a live. If we go to grade and it's down, that's, there might be some flexibility. I don't know. Depends situations and everything, but it's got to be up. Objective 2, email verification. To create an account, you should also have an email address. You have username, email, and password as your registration form would be the ideal way I shouldn't say ideal, but the expected way that you would do it. Or once you create a profile, you can go to your profile page and enter an email address. When you enter an email address, it should say that it's not verified. We should be able to either click a button or just have it happen automatically, that you'll send an email to that email address, and then that email will have a link, the verification link. You've seen these as end users before, I'm sure. But it'll email you a link with a very random generated URL. And then when that URL is visited, that email is then verified. So have something to verify email addresses, and then at that account, it should say email address verified. So that's objective 2. It's expected. You can use whatever you want, however you can get this done, but it's going to be expected, and I'll demo in lecture how to do this by linking a Gmail account using the Gmail API. I wanted this to be running your own SMTP server, but as it turns out, that's not quite feasible in the internet these days. It used to be more feasible. And then some very basic DOS protection. This isn't going to be like actual DOS protection. You're still going to be vulnerable to DOS attacks. But some DOS protection, we're going to do this by IP rate limiting. So if an IP address is sending way too many requests way too fast to your server, cut them off. Specifically, if you have more than 50 requests over a 10-second period, you should rate limit that IP address and rate limit them block them for 30 seconds. And then after 30 seconds of being blocked, they will be unblocked and they can send requests again. So that's the last objective. And that's it. That's going to be the rest of the project. And then I haven't talked about presentation. I have to get the presentation document up too. I keep slipping my mind because I was focused on part 4, getting part 4 out. But the presentation, you'll demo your live deployment of your app, and that's when we're going to at least somewhat load test your app. And by load test, it's going to be the most basic implementation of that phrase is you'll put your URL up on the projector, and then everybody in the audience can go to your app and use your app. If it can handle that load, you'll get full points on the presentation. So you'll demo your app, you'll use your app, and then say, here's our URL. We use your app. If it holds up, full credit. If it doesn't hold up, then there's a rubric, and I'll release that. I think it's. I want to say 3 AOs, but let me just double check before I say something wrong. Six. Oh, so I just multiplied it by 2. So 2 AOs by demoing your live deployment, going to your actual link and showing, hey, the project works. Oh my goodness. I think I did forget. Shit. I think it's 2 more if it just kind of works, and then 2 more if it works for the load test. But how do I distinguish between works and kind of works? I'll have to really look at my rubric. I already have the rubric. I just got to release the document. Forget exactly how I worded it. But there's 3 tiers. It working for you, it working for a few people, and then working for everybody going to it. But yeah, that's where we're at for the rest of the course. So let's get into it. One of my favorite topics, encryption. My goodness, the internet here. Are these objectives in order of difficulty? Oh, you know what? I don't know if I thought about that. For project part 4, the difficulty of them. Yo, I didn't retest this. Damn it. I pushed, but I didn't make sure the new one worked. I exported to PDF. Because I pushed it to the 116 website. This is why I pull. This is why I do this. That's why I like downloading the slides right before lecture, so I can catch things like this, so y'all can have the slides too. Okay, so that's gonna take a hot second here, but bless you. Maybe I can start with my demo, I guess. I need a website that uses login. Any website. Twitter? Let me hit the brakes. Private window. There we go. What? I just want to type a username and password. Here we go. Okay, when I type a password, no matter what site y'all shout out, we can do another one if you want. Whatever we're using to log in, any site that you use, I promise I'll get to the end of the sentence. I gotta figure out. Is going to send your password in plain text. Your password is going to be sent in plain text over the internet. Which is something we're always told, don't do anything with passwords in plain text. But any site you shout out, we can go to another one if you want, is going to send that password over plain text. Doesn't matter which one. I've never had in lecture somebody shout out something, I went to it and then said, whoa, they're actually not sending in plain text. They send it in plain text. Yeah. Well, I mean, I didn't type my real password, but if you type in your real password and actually log in, that request that's sent to the server, that password's going to be in plain text. All the time. Like when this request was sent, they didn't check if my password's right or wrong yet. Not until the server gets the request, then it can verify. Every site is going to send that password in plain text. Hey, we have slides. Okay, now we're in business. Only 15 minutes in. I introduced homework in project part 4 too, though. Okay, so let's talk about encryption. Encryption, don't worry, your passwords aren't insecure in that way. We are going to talk about encryption. We do have an answer to this. Not like literally every site you go to ever isn't just leaking your password. But let's talk about why that is the case and why we're protected against it. Encryption. So the problem is we send messages over the internet and people can see that information. And this does include your passwords, as I got the demo there. I usually get a few slides in and then demo that. But this includes your passwords. Your passwords are sent over the internet in plain text. That happens. That's the reality of the way we use the internet these days. And okay, so who has access to those packets? Who's going to see those packets and start reading that information from me? Your ISP, yeah. I mean, you have some level of trust or mistrust with your ISP that you can deal with. UBIT on campus, they have access to everything. I mean, we're using their hardware. They have access to that hardware. They can monitor our packets. That's something they can do. The Tier 1 networks that you don't even have any affiliation with, but UB pays Tier 1 networks for internet access. Your ISP pays Tier 1 networks for internet access. They can all see your packets flying through the air. But there's a presumed level of trust with all three of these. Maybe you don't actually trust them, but there's a presumed level of trust. At the very least, personally, I trust all three of these to the extent that they don't want to damage their reputation. They don't want to be on the news for stealing my password and posting dumb things on my Twitter. They don't want that static. They have more important things to worry about than messing with me. So there's some trust, some mutual, shouldn't call it trust, but like some mutual thing there. Like they're not going to destroy themselves to destroy me. They don't want mutual destruction. I think that's the word I'm looking for. But there's another entity that has access to your packets, and that's every single person in Wi-Fi range of your device. Wi-Fi does not work with beams. When I'm connected to this access point, there's not a beam of data going to that access point and a beam of data coming back to my laptop. Both of these devices are broadcasting my packets to all of you. When I send something from my laptop, including that request that can include a password, it's going in a huge radius. I shouldn't say huge, but a pretty big radius that's hitting every single one of your network cards. And your network card says, this packet isn't made for me. I'm going to throw it away. I'm not going to use it. But that access point is saying, oh, this packet, I have to do something with this packet, and it's going to forward it off to the internet, out through UB's network, out to the Tier 1, and off to wherever it's going to. But you can read those packets. Like your network card is your property. You can configure it to give you all this information. You can install something called Wireshark. Some of you have probably done that already. That will show you all of the packets that are hitting your network card, whether they're made for your device or not. And you can just sniff all those packets out of the air and see what everybody's doing on the internet. Everybody within Wi-Fi range of you. This, you better not trust this entity. These ones, fine. You can make a reasonable argument, my assured, mutual destruction argument or whatever. This one, no. Never, ever. Especially when a lot of times you find yourself in a room full of computer science students who might know what to do, how to do this stuff, and then what to do with the data to attack you. No, do not trust everybody in your Wi-Fi range. My goodness, do not. So that's the problem, is everybody can see what you're doing, including your passwords. And I did the demo, but why does this include our passwords? Why, did everybody just lose their freaking minds and say, we're sending passwords in plain text? Why are passwords sent in plain text? Yeah. Not that I know, not off the top of my head. Wireshark has a nice interface. Honestly, every time I've used Wireshark, even with the interface, I get lost. There's so much data, so much hitting your network card. It's ridiculous. I wouldn't want to use a command line tool. But if you're really good at grepping, maybe. Oh, I didn't do an order of difficulty. I'll let you think about this for a second. Well, I haven't thought about the order of difficulty for project part 4. I think the first one's not too bad. The first one's, again, I have the demo that I go through, at least for the homework, and I don't know if I'll find time to do the demo for the project. Maybe I'll try to jam both of them in Friday. But I don't think part 1's that hard, aside from actually deploying, actually getting a domain name and everything. I didn't mention it. It's in the document, but there's the GitHub developer pack where you can get a free domain name. You can get a time on a DigitalOcean droplet. You should be able to do everything with that objective for free. If you can't, if everybody on your team has already used all of your credits for your GitHub development pack, or for whatever reason you're in a situation where you have to pay to deploy, come talk to me. I don't want anybody to have to pay to deploy their app. You should be able to do it for free. If you can't, let me know. But you can deploy, and it's not too bad. Email verification, I don't foresee being too much of an issue. It's a little bit of work, but you've already built an auth system. It's not too much more coding to build the email system. And using the Google API, I'll demo that in lecture. I'll show you how to use it. I don't think that one's going to be too bad either. It'll be work, sure, but it won't be terrible, especially when you have a team of people, if you're in one of the teams where everybody's working anyway. But and then part three is going to be pretty tricky. Part three is definitely going to be the most difficult. Maintaining this sense of timing is going to be pretty tricky. How many requests in the past 10 seconds and then the 30 seconds, that's going to get tricky. But then again, you've already gone, by that time, you'll have already gone through part three, where unless you're building the game, you already had to build some sense of timing and have to be aware of time. So if you've gone through one of those in part three, that one maybe not too bad. But if it's your first time doing timing, it can be pretty tricky. Yep.
The email verification, can we and are we allowed to use standard mail message protocol or not?
If it works, it has to work, and we have to actually get the emails. Like, our email server can't reject those emails and mark them as spam. If it works, it works. But I should add that to the document, that if it gets filtered to our spam, I don't want to say that in general because I can see that happening for legit reasons, but it shouldn't have like security warnings on the email that you send. That's not going to be okay. I'll have to add that. There can't be security warnings on it. It has to be a legit email that can be verified. Or else I'm clicking on some random link that could have been sent by an attacker. So why are my passwords being sent? Why are all of our passwords being sent in plain text? Why not hash them? Yeah. What do you mean check it, though? Kinda. So the attacker won't. If an attacker is sniffing packets is on and don't have access to your device, they wouldn't be able to see that being hashed. They wouldn't be able to monitor the hashing process, so they wouldn't be able to see the original password, but they will see this hash flying through the air. So why wouldn't we do that, though? All they can see is the hash. They'll never know your password, ideally. Yeah. Then we'll hash it again when it gets to the server. So I'm a clever security programmer. I'm going to hash client side. When I get to the server, I'm hashing it again. Then I'll hash it a third time just for fun. Yeah.
Hashing uses a lot of resources, takes time. Why would you do that there?
Yeah.
Do it on the server?
We're getting, so that's part of the answer is there is a cost to hashing. It's not absolutely free. So if we got anything at all out of this, if we got any added security from hashing, everybody would be hashing. We'd probably eat the cost. The fact that nobody does tells me that there's nothing at all to gain. So why isn't there anything to gain here? Yeah.
Theoretically, if you're hashing on your front end, any user with usage requirement can see how you do it.
Yes.
So when they know how you hash it, they'll be able to
Mm-hmm. Yeah, so everybody would know because everybody can look at your front end code, so they know exactly what you're doing. So there's no obscurity there. But they'd still have to break a hash, so you can figure out which hashing algorithm you're using. So why don't we gain anything by hashing? So if my front end, my JavaScript, is going to take this password that you entered, hash it, and then send the hash to my server, what's my server expecting as the password for this user? The hash. Server's expecting that hash. If the server sees that hash, it's going to say, you're a legitimate user, you're in. So if an attacker looks at this hash flying through the air, they grab this hash, they send that hash. They're going to ignore like the form. They're not going to fill out the username and password in the form. They're going to send a request, a handcrafted request, with that hash. Server's going to say, oh yeah, that's the hash I was looking for. You're in. You got it. And the attacker doesn't actually need to know or care what your actual password is, what you typed into the box that went through the JavaScript. As long as whatever happened there, I don't care what happened there, whatever spit out the other end, as long as I have that and I have whatever the server's expecting in place of your password, I'm going to use that and I'm going to send that and be authenticated. So we don't gain any security by hashing before it leaves the client, as long as the attacker can simulate whatever the server's expecting, and that's what has to go through the air. So why not just make that the password? The hashing doesn't actually help. Where hashing hurts, we actually lose something by hashing, is the server can't do any server-side checks on password strength. All the password strength would be verified client-side, and when do we trust our clients? Never, never, ever trust them. So there would be no password strength verification if we sent hashes. So we would lose something, we don't gain anything, and we would use more resources to do everything. So passwords, plain text. Always, anything. Any site you try. Okay, so how are we secure? Well, crap. We're sending plain text passwords. That's just the way it works. How are we even secure at all? We're going to take an S. We're going to slap it on the end of our HTTP and call it a day. We're done. So we're just going to encrypt everything. So HTTPS, usually called HTTP secure or secure HTTP. What it actually is, I'll probably mix between the two. But HTTP over TLS is what we use. And TLS adds a layer of encryption. So we're going to encrypt everything. So yes, your passwords are in plain text. When I view the requests that I send in my browser console, I can see the password in plain text. But before it leaves my device, it's going to be encrypted. So if you're sniffing my packet out of the air, you just see a bunch of crypto text, and you can't actually read what my password is. Then the server receives it, decrypts it, and can see my plain text password. So the server will be handling my plain text password again. So as long as that server isn't compromised, and as long as somebody's not viewing the registration or login process, because it will be plain text at that point, then they're not going to be able to recover that password. So they either have to compromise my device or the server on the other end. Going through the internet itself, we're going to be encrypted, so we're going to be secure. Yep. There is a cost, but everyone does use it. Like these days, any site you go to is going to be HTTPS, for the most part, I should say. Ever since, it was years ago by now, but Chrome, Google, they decided that they're going to give browser warnings if you use HTTP. So if you're not using HTTPS, the browser says, are you sure you want to be at this site? And nobody wants that on their site. So it's really built a culture where just every single site uses HTTPS now. There shouldn't be anything using just HTTP anymore. I used to have examples. I go to lecture and say, here's a site that uses HTTP. This is what you see. I ran out of examples because they all started switching to HTTPS. Everything's encrypted. And you can see that if you go to if you see this lock here, and you can see all the HTTPS settings, or if you go to the console, aside from your homework site, and your project site at this point, I guess. If you look at any of the protocols, it's always going to be HTTPS. You're going to be hard-pressed to find a site that uses HTTP. Everything's encrypted out there now, which I'll say is generally a good thing. Yeah. Wait, what was that? Yes. Yep. Yeah, that's in TLS. No. Because of math. is actually going to be the answer. Well, I got a bunch of slides on it. We'll talk about it. But the short answer is the server is going to generate a public-private key pair. We're going to encrypt with their public key. And then without that private key, which they should be holding private, nobody should know that. Nobody can decrypt this traffic. So it's encrypted with different keys depending on which server you're communicating with. Okay, so this is what we want. For encryption, I want to send a plain text message to somebody, which might contain my password. I want to send this plain text message. It's going to be whatever it actually is. We communicate all kinds of information. And it's called plain text, but it could actually be bytes. It could be an image. If we're encrypting text, we're going to convert it to a byte array and then encrypt it. It's all going to work with bytes. So we want to encrypt our plain text to generate a ciphertext. At least that's what I call it, and that's how I spell it. It's different no matter what resource you're looking at. But I'll call it a ciphertext because that's how it was first introduced to me. And nobody should be able to read this ciphertext except the intended recipient. That's our goal. Nobody can decipher it. Nobody can get back to the plain text unless they're the one that I specifically want to be able to read that text. And the intended recipient can get back to the plain text. These are the properties that we want from our encryption system. So if I have some message I want to send to somebody, I'm going to encrypt. It's going to encrypt to some crypto text that's just absolute garbage to anybody except the intended recipient. The intended recipient should be able to get this, decrypt it, and get back to my original message that I wanted to send that person or that server. Is there any particular reason why localhost runs on HTTP instead of HTTPS? You can, and for homework 4 you will use localhost with HTTPS. The only reason we haven't yet for homeworks 1 through 3 is we just haven't gotten to this content yet in the course. You won't actually use HTTP for homework 4 or for project part 4. Everything in part 4 is going to be encrypted. So we are getting our HTTPS on from here forward. But there's not inherently with localhost and HTTP. It's just how we've used it so far. And the answer to this, one answer to this, I should say, is public key encryption. So public key encryption, this is the idea that I briefly mentioned just now. We're going to have a private key and a public key pair. The private key, as the name implies, should be kept private. Whoever's key pair this is, they take their private key, they put it in their pocket, they don't let anyone access that. This is my example from way back when, but arbitrary file requests. In our image path, we have to handle these requests for images, and then I said the slashes in your path, just get rid of the slashes. The first example that I did was a request that would access your private encryption key. This is something that needs to be private. Don't let somebody request your file that contains your private encryption key. And then the public key, as the name implies, this is shared with anyone and everyone. Everybody gets to see your public key. No exceptions. Everybody is just out there. Once you share it with one person, you have to assume it's compromised. It's just able to be shared with everybody on the planet. And then whenever somebody wants to send, so I'm a server, I want people to be able to send me encrypted messages. I generate my private key in my pocket, public key to everyone. And if you want to send me a message, you take my public key, encrypt with my public key, send me the message such that it can only be decrypted with my private key. So I can read it, but nobody else can. And that's the idea with public key encryption. And these keys are inherently related. The public key and private key have to be related in some way. And the way we're going to see, it's going to be mathematically linked. It's all a bunch of math when we're talking crypto. These keys are linked, so we need a couple of private properties here. An attacker who has my public key can't compute what my private key is. They are linked. There are a lot of properties in common. There's similarity between them. They shouldn't be able to find out what my private key is. And an attacker with a ciphertext and my public key shouldn't be able to decrypt it no matter what other information they have. If they don't have my private key, they shouldn't be able to decrypt that ciphertext. So these are like the two major properties that we want that determines that this can't be broken. And there are many others. There are a lot of other properties that we want, but these are the two major ones that we'd focus on. If we don't have both of these, we don't have a crypto system. And RSA has these properties. So let's talk about one specific crypto system, one specific public key crypto system, RSA, which is going to have the properties that we want. We're going to look at 3 algorithms, one to generate the key pair, one to encrypt, and one to decrypt. And we hope it works. We hope. So this is key generation. Fits on one slide. It's actually not too crazy. It's some math and stuff, but it's not the craziest thing. For what we get out of RSA, it's surprisingly simple, even if it's not objectively simple. But it's not like you have to take a whole course to figure out how to do this. You stare at this slide long enough and you understand how it works. So we're going to generate 2 large prime numbers, P and Q, multiply them together, call that n. We're going to define a value lambda of n, which is the least common multiple between P minus 1 and Q minus 1. We're going to choose some value e that's both less than lambda and is co-prime with lambda. So meaning the greatest common denominator between them is 1. We call that co-prime. And then compute d, which is the inverse of e mod lambda. Once we do all this, we have all our values that we need. And all we did was choose 3 things, P, Q, and E. These are the 3 values that we chose when we're generating our key value pair. And they're randomly generated when we run code that generates our keys. E and N are our public key, really I guess both. E and N are our public key. We share those 2 values with everybody on the planet. D is our private key, and the rest of the values we can just throw away. They were just used as intermediate values while generating our keys. So that's our key generation. And you could compute this. It actually used to have as a 199 assignment that students would actually go to Wolfram Alpha, choose a P and Q, choose an E, and generate their own public-private key pairs, send me an encrypted message, and then as long as all the encryption was valid, that would be their assignment. They'd get credit. It's not too hard. Freshmen can do it. Not securely. I had them choose very small values, so it wasn't secure, but and then to encrypt or decrypt, if I want to encrypt plain text M, a message M, I'm going to raise it to the E mod N. E and N are the public key. I have both those values. M is the message I want to send, so this is just math. That's going to compute my ciphertext. And when the server wants to decrypt my ciphertext, they're going to raise it to D mod N, and that's going to give them M. That's going to get back to the original text. So as long as nobody has D, the private key, nobody else can decrypt this. Yeah.
So is M in bytes?
M would be in bytes, and then you have to chunk, M has to be smaller than N. So if you have a large message you want to encrypt, you have to encrypt it in chunks. I'm not 100% on those details, but it needs to be encrypted in chunks. But M is a number. You convert it to bytes, and then convert the bytes to a number. Yeah.
So you said that each key is just a large prime number, right?
Mm-hmm. Well,
Relatively, what is the scale of those numbers?
2K bits is usually, or 4K. Sometimes they go up to 4K. My demo, I'm going to use 2K bits. So on the order of 2 to the 2,000. Large. Big, yeah, very big, very large numbers we're talking here. Oh, I already read that. And this actually gives us a really nice property. So if you combine encryption and decryption, we have M to the ED mod N is going to give us back M. And since multiplication is commutative, we can reverse the E and the D. We can either encrypt with the public key and then decrypt with the private key. That's the method that I described. Or we can do this the other way around. We can encrypt with the private key and then decrypt with the public key, which I have to put in quotes because we call this a signature. You have a digital signature using public key encryption. This is how it works. We don't call it encrypt if we go that way, because if I encrypt with the private key, who can decrypt that everybody on the planet. Everybody has my public key. Everybody can read that message. There's no security. There's no privacy here. But I can sign with this. So we call this a digital signature. I sign with my private key, and you verify the signature with my public key. So this is how we sign things on the internet, to verify that it was me that wrote that message. If it was signed with my private key, which means you can take my public key and the signature verifies, and usually we sign a hash. We take a hash of the message and then sign the hash. So if everything checks out, you hash the message, and then you take the signature and verify it with my public key, and those two hashes match, then you verified the signature. So this is how we sign. A nice benefit of public key encryption. Don't just use it to encrypt. We get this nice side benefit, which is nice to have. But what about a brute force attack, you say? Everybody has my public key. This is what we did with hashing, right? Everybody has my public key. They retrieve a crypto text out of the air. They take the public key, and they just take a bunch of guesses. They take a guess, encrypt, bless you, check if it matches the crypto text. Take another guess, encrypt, see if it matches, bless you, see if it matches the crypto text. They just keep doing this until they crack the encryption, right? If I ask a yes or no question and somebody responds with either yes or no, but they encrypt it, there's 1 bit of entropy there. They can take at most 2 guesses. Actually, after 1 guess, you can infer that's the other one. But 2 guesses, and it's done. Like, there's no encryption there. Bless you. There's no encryption there, right? There's no security there, right? Wrong. We actually have an answer to this. There is an answer to this. We don't have a strong answer for hashing, but we do have a strong answer for encryption, and that's a padding algorithm. So instead of just taking the message that you want to send and encrypting it and sending it, what we do is add random garbage to the message. We take our message, we add a whole bunch of random garbage called padding to the message, encrypt the whole thing, and send it to the other user. Now, anybody trying to break this crypto text needs to guess all of that random padding in addition to the message, and we add enough padding that the entropy is so high that they're never going to be able to do it. They'll never recover that message. They'll never guess all the padding because we're going to add more than 80 bits of padding to this thing. And this, unlike salting, does add entropy, does add actual security to the message to the point where even with that yes or no response, we can send 1 bit of data securely using encryption if we have a properly set up padding algorithm. This does actually add security. So why? I kind of want to just leave this as a thought exercise. I do have 1 bullet point here. Why does salting not add entropy, but padding does? And it's because with encryption, we're actually going to decrypt. The recipient is going to decrypt, and what they can do is decrypt. We'll add some delimiter to the message that says everything after this point is random garbage that's part of my padding algorithm, and they just throw that part out. It's no big deal to an actual legitimate user. You just throw out the padding. Done. And then take the message and read the message. But an attacker can't do this, and we can't do this with salting either because the hash is never unhashed. We never go back to the plain text password where we can say everything after this is the salt. We can't do that because hashing is made to be one way, and encryption is made to be bidirectional. We can decrypt. We can't unhash. We can decrypt. So there's a big difference between salting and padding. Padding adds tons of security. Encryption is really, really secure, as it turns out. Where hashing, we still have to rely on people giving us good passwords. Okay, another problem with this. This is all just math, right? We gave everybody E and N. So everybody has N. Everybody has E. With N, if they can factor this to figure out what P and Q are, they can compute lambda of N. They already have E, so now they can compute D, which is the private key. What's stopping people from doing this? It's all just math. There's one step there that, as it turns out, is way harder than we'd ever think, or at least that I ever thought, is that factoring is super duper hard, which is an official term. It's super duper hard. At least we hope it is. So there's no publicly known algorithm. There might be somebody who can efficiently factor that just isn't telling anybody and is out there breaking everything. But there's nothing publicly known about this yet. So we hope factoring is really, really hard. And specifically factoring the multiplication of two primes, which is exactly the way this is set up. RSA, it's set up to be the multiplication of two very large primes on the order of 2k bits, as we said. Then it's actually really hard. There are some known, worrisome things in the future. Quantum computers can factor efficiently. If we ever get a 2k bit quantum computer, then things can start falling apart here. But until that day, we're just relying on factoring being a pretty hard thing. And we call this a cryptographic primitive. If you can prove that breaking your crypto system is equivalent to solving a cryptographic primitive efficiently, we call that a pretty good crypto system. If factoring's broken someday, then the whole thing falls apart. But until then, if you can prove that breaking your system is like factoring, then you're looking pretty good. And there's another problem. We send this message, this crypto text. This crypto text is C equals M to the E mod N. You have C. Well, if you can compute the discrete log of M mod E, you can compute the discrete log base E of C mod N. I said it backwards. You can compute M. This is a logarithm. It's discrete log because it's using modulo arithmetic, but it's still just math. And good thing for us, we think this is pretty hard too. Computing a discrete log is hard, especially with these numbers being so large. Discrete log is another cryptographic primitive, so we're good there too. If either one of these cryptographic primitives is